look at discrete and continuous variables. So, well, let's get right in with the discrete and continuous part, and then we'll look at probability distributions that use them. A variable is discrete if it can only take individual values. Now let's try and give you an example of what I mean by that. A variable is just something you're measuring, right? So you could be collecting data on the heights of people, the weights of people, how many jobs they've had in their life, various things. Now, those things you're collecting, that's our variables. They can fall into two categories. The first one is the discrete. So if I say it can only take individual values, that's just my way of saying it has to be something that can only be this number or that number or that number. It can't be any number between the two. So example, you can have one child, you can have two children, you can have 0 children. You can't have 1.1 child, right? So 1, 2, 3, 0, 1, 2, 3, that's discrete. Number of coins in your pocket is discrete. Try to think of the number of countries you've visited in your life is discrete. The number of jobs that you've had in your career is discrete. Does that kind of make sense? What would be a discrete variable?
Yes.
Right. So if you have only got a discrete variable, then the probability distribution tends to be done in two forms. You tend to get either a table or you can get a graph to represent it. So let's give you an example of what that might look like. Suppose we do a story with 2 coins. And you throw the first coin up and it's a head or a tail, you throw the second coin up, it lands a head or a tail. The variable here is discrete. It can either be a head or it could be a tail, right? There are only 2 choices. And so you might have, a way of counting this might be to do a table that looks something like this. So that mess in there says outcome probability. Well, you could have, oops, what am I going to do? There we go. You could do 2 heads. You could have a tail and a head. You could have 2 tails. Now you notice that my table has 4 slots, but I've only filled in 3 of them, right? Both of them were heads, both of them were tails, and then the third one, the one right at the bottom, says tails and heads. There is a 4th possibility that can happen.
Head and tails.
Yes. So we have to be aware that when you do these types of probability, the order in which something happens makes a difference. A head first and then a tail second is considered a different outcome than a tail coming first and then the next time it's a head. Now, each one of these probabilities, you're just going to trust me, but it's easy to calculate them. They all end up being 1/4. For instance, to get a head is a half times another head, which is another half. 1/2 times 1/2, and you've got a quarter. That makes sense?
Yes.
Right. Now, you can also create a table with this data in a slightly different version. You can have outcome and probability. and you can have 2 heads, 1 head, and 0 heads. In fact, they probably wouldn't even put the H there. They'd probably just say outcome, number of heads, and just leave that as a 2, a 1, and a 0. Well, suppose the outcome was 2 heads. That can only happen 1 in 4 times, right? 0.25. What's the chance they get 0 heads? Well, you know, 0 heads is just another way of saying they were both tails. And that can happen 184 times. But what's the chance that you get 1 head? Well, isn't there that guy there is getting 1 head and a tail? And isn't this guy getting 1 tail and a head?
There's 2.
So there are 2 then, which I'm going to simplify down to half. Now, these are both examples of probability distributions where the variable was discrete, right? I think the homework likes coins being thrown in the air, boy, girl, children and family kind of stories, and I think they like something to be attack where it lands up the way or it lands down the way, right? That's the main kind of discrete versions they've got. Now, I did say you could get a graph. And the graph might look like this. Along the bottom, number of heads. So we're going to use this data. And the vertical is always going to be the probability. And then I don't know if you've seen a graph like this. It's kind of weird looking graph. Once you've seen a few, you get used to it. 0, 1, and 2. So that means 0 heads, 1 head, 2 head. And then, let's say that's a quarter. Let's say that's a half. I guess you could go up to 3/4. You put a dot there and a little line. You put a dot there, a little line. And you put a dot there, a little line. So this is a graph of a probability distribution. What it does is it shows you all the things can happen and the probability of those things happening. Does that table, well, it's a bit weird looking, especially with the line and the dot. Does it make sense how that could be created? Are we any issues with that, or can I move on?
No, sir. Okay.
We're good? Right.
Yes, sir.
So before I leave this, the discrete stuff, because there's not too many more things left to do with discrete, at least the start part is. Let's suppose I have, I'll start again. I'll do my table first. Suppose we have a discrete thing, whatever it could be. I'm not even going to put details in because that's not important for this question. And I tell you that this fella is nothing 0.2, 0.5, 0.1, and 0.3. And the question is dead easy. I mean, it's a simple question to answer. And that is, could this table be a probability distribution? And you answer yes or you answer no. So we've got 4 things that could happen, you know, like 1 head, 2 heads, 3 heads, 4 heads, whatever it is, right? We've got 4 things that could happen. And the probabilities of each of those 4 things are written here. Yet this cannot be a probability distribution. So what is the problem?
I don't know.
Right, well, that's fine. I'm going to show you next time you'll see it. So, Raven, you're watching? Your hands are in the air, so I'm not quite sure what you're watching. So, in this table here, the reason this doesn't work as a probability distribution is 7, 8, 9, 10, 11. If I add them up, I get a grand total of 1.1. Do you know that all the probabilities added together should always come to 1, right? 1 means everything, right? Everything's covered. So if this number, the total, is bigger than 1, it cannot be a real probability distribution. You've screwed up in one of your calculations.
Oh, yeah.
That makes sense?
Yes, sir.
Yeah, right. So when you're doing, because maybe one of your jobs might be to create one of these tables, you can use that as a quick check. Shouldn't you add up all the probabilities? And if they come to 1.1, you're going to say, nope, I better go and check my calculations because at least one of them is wrong. And it gives you a way to do that. What's wrong with this one then? It does actually add up to 1, but it's still not a probability distribution.
Yeah.
It has, right? What's wrong?
Because probability is between -0 to 1.
Right, just, well, 0 to 1, right?
Yeah.
And you're not allowed
Oh,
negative
0 to 1.
numbers. Yeah, you're not allowed negative numbers. Probability of -0.2 has no meaning. It's a bit like saying, 0 is the worst probability in the world for an event because it means it's never going to happen. Well, negative 0.2 has no meaning, right? It doesn't make sense.
Yeah, it will never occur.
Right, you'll never get harder than it ain't going to happen. So are we good?
Yes, sir.
Right. So let's move on then and look at. Oops, I'm having. Oh, she's sitting by the door. That means she needs help. Off you go. Come on. There she goes. Let's try again. And we are looking at the second kind then. Continuous variables. So there are only 2 kinds of variables in the world that we need to worry about for probabilities. We've looked at the discrete one, right? That's where the answer can only be A, B, C, 1, 2, 3, head, head, tail, tails, right? There can only be fixed, finite in number of them typically, right? So far, so good. So what does continuous look like? Well, this is when the variable can take any value between 2 fixed numbers. And this is just my way of describing it. I'm sure there's better ways, but this is the way my brain works. So give an example. If you take someone's height as your variable, you might say, and you're 62 inches, somebody might say I'm 63 inches. But theoretically, can't you be 62.1 inches? And if you had some really, really accurate machine, couldn't you be 62.1, 2, 3, 4, 5, 6, 7, 8, 9 inches? In other words, theoretically at least, can't you be any number between, 61 inches and 62 inches? So your height would be a continuous variable, right? You don't go from 60 inches and then you wake up in the morning and now you're 61 and it just like, boom, it jumps, right? You grow all the way through 61 to 62, right? As you get older, when you're a younger person at least. So examples of these, well, your height. Your weight. What I would just say to myself if I'm thinking about, is this thing continuous? I'd just say, let's put a number on it. Let's suppose that a bag of potatoes could weigh 3 pounds and a bag of potatoes could weigh 4 pounds. And then I say to myself, can a bag of potatoes weigh any number between 3 and 4 pounds? And I'll say, yeah, it could be any number, right?
Right.
That makes it continuous. Anybody want to throw in an example of another continuous variable just to get the feel for this? Any thoughts?
I'm thinking.
Oh, thinking is good.
Not the age. Not age.
Oh.
Age is exact number.
Well, see, you got to be careful about that because I can see where your problem lies. If you say to someone, "How old are you?" I'm 42, which I wish I was, right? I'm 42. And you ask someone else, they say, "I'm 43." But really, if you delve into it, you're not really 42. You're
Like
42 and 3 months and
Yeah.
2 days and 4 hours and 6 seconds. And then couldn't you just keep going 6.1, 2, 3, 4, 5, 6 seconds, theoretically, right?
Yeah, yeah.
So, yeah, your age actually does count as continuous.
Oh,
Even although human beings don't normally use decimal values when they talk about your age.
yeah.
But I know 5-year-olds do. Don't 5-year-olds say I'm 5.5 or I'm 3.5? I mean, they like that extra half, don't they? So in a way, children kind of measure age a little bit better than we do. Anything else? No, let's. Jamie got hers. What's you got, Raymond? Something that's continuous. Something you could measure that's continuous.
Oh, there it is. I'm on my phone and I've never
Oh, okay.
find the new something that's continuous that
Yeah.
you can
Something you can measure that's continuous.
the height of a plant.
Oh yeah, I guess that counts as height. That's a specific one. So I'm going to change it to the length of a plant because you put on its side.
I have one more, sir.
Yes.
Mileage.
Oh, the distance you did in miles.
Yeah.
Yeah. So I mean, if you think about it, there's a fair number of things out there that you can measure that are continuous. And there's a fairly large number of things out there that you can measure that are discrete. And I think in a funny sort of a way, discrete are easier. It's easier to think of things that you can only get, 1 kid, 2 kids, 3 kids, right?
Mm-hmm.
I've only been married once, twice, or 3 times, right? I've only been married once, I'm glad to say. And so on and so forth, right?
Right.
So we're comfortable with the difference between discrete and continuous.
Yes, sir.
Now, remember we did the probabilities of distributions of discrete, and you could either get tables or you get a probability distribution graph, which is this. So how does that look when you're talking about continuous variables? You can't really, and you never will, do a table like this, right? You can't say the probability that the bag of potatoes weighs 5 pounds is a tenth, and then 6 pounds it's a tenth, because what about the 5.1 pounds and the 5.2 pounds? You say it doesn't really make sense to do that. All you can do is you create a table, basically a diagram, I should say, that looks something like this. Now the vertical is still called probability, and the thing along the bottom is going to be the variable. So I'm going to pick, my variable is temperature, right? And so can you imagine there was a place where they collected information, say, about the temperature. Now, the temperature could be 60 degrees, it could be 61 degrees, but it could also be 60.2 degrees, right? So it's continuous. Temperature is continuous. And let's suppose that we have a place where the temperature is 60, right? And over here, the temperature is 70. And we've got this little rectangle, and this rectangle has a height of 0.1. That is what the probability distribution of a continuous variable might look like. This is a very simple picture. I just made a big rectangle, right? But it could be a triangle, it could be curved. What makes it important, or how does it work? The total area of the shape must always equal 1. So if I check this, 10 degrees times 0.1, do you see that does add up to an area of 1? Now you may think, how can you use that picture to get any kind of probabilities? Well, when you do continuous probabilities, you tend to write them like this. What's the probability that the temperature in this place is greater than or equal to 62? So can you imagine that there's this, I don't know, some island in the Mediterranean where the temperatures range between 60 and 70. And you'd like to know what's the probability that you turn up on a particular day and the temperature is at least 62 or better. So what you got to imagine is there's 62. And the probability that you get a temperature, X is just short for get a temperature of, greater than or equal to 62, is that you need to find that piece of the cake. So imagine the whole probability distribution is the entire cake. Individual properties end up being pieces of that cake. Now, in this question here, since the shape is relatively easy to see, would you agree that the distance from here to here is 8? Right, 62 to 70, right? 8.
Yeah.
Isn't the height, in this case, always 0.1? So the chances, the probability of that happening is 8 times 0.1, which is 0.8, which I'm going to call 80% because I like percentages for probabilities, although I'm not sure the textbook does. There's an 80% chance that if I randomly turn up on that island sometime in the year, there's an 80% chance that when I do that, the temperature's 62 or better. So do you see how this picture can be used to calculate probabilities of continuous events? But continuous events are now going to be X bigger than a number, X less than a number, or X between two numbers. Right? So the probability questions that you get asked are slightly different than the kinds of things that you get asked when it's discrete. When it's discrete, they say, what's the probability that you have 2 children in your family? What's the probability that you've had 4 jobs? What's the probability that you've got 7 coins in your pocket? You see, in those questions, the probabilities can be and very often are single things that you evaluate. But when it's continuous, you can't say, what's the probability that your height is 60 inches? Now, a lot of people think that makes sense, but you got to go a little theoretical here. What's the probability that you are 6 inches? Not you particularly, but just a person in random that I picked in the street. Well, you might think, yeah, there's a certain percentage of Americans who are that height, so that must be my chance. But if you delve into it, if I pick somebody at random and I measure them, are they truly 6 feet? Or 6 inches, I should say. Well, not really, no. See, if you measure them really, really accurately, couldn't they be 60.002 inches? Or 59.99999, 2 million more nines than a 1? Theoretically, do you see the problem? Continuous information can't be evaluated as a single number in the usual way that we would do. We only evaluate them in greater than, less than, or betweens. So let me show you a less than then. And I'm going to cheat a little bit. What's the probability that I turn up to this island and the temperature is actually less than 62? Right, less than or equal to 62. Less than or equal to 62 is this piece of the cake, right? And this piece of the cake is 2 that way, multiplied by 0.1 the other way. And so we get 0.2 or 20%. We agree?
Yes.
Now I'm going to have to do another picture for my last version. if you write something like this down mathematically, you know this funny X in the middle with a less than or equal to either side and then a 61 at the beginning and a 64 at the end. Have you seen that? I mean, it's a you may have seen it in, if you did 141, you would have seen it, but you may not have seen it before. Do you know what that mathematically is just saying? X is between 61 and 64. Right, so in English, you would just say, oh, what's the chance that I turn up to this island and the temperature is somewhere between 61 and 64? Does that make sense? So that's how you would phrase a between. Right, you notice bigger than 62, less than 62, or equal to, between 61 and 64. Well, let's look at my little picture here. Do another version of it here. There's 60. There's 70. There's the 0.1. That's the whole cake, right? The 1, the area of 1. Now, if I want to do a 61, let's say it starts there. If I want to do a 64, let's say it finishes there. Can you see the piece of the cake? Is that guy. Now, if you want to get the area of that piece of the cake, can you see that 61 to 64 gets me 3 times the height of that cake? 0.3, 30%. So when the data is continuous, it has a picture like this associated with it. This picture has the property that the area of the shape must always equal 1. But once that is true, you can then calculate probabilities that you pick something bigger than 62, less than 62, or between any two numbers you like. I could even go weird numbers. Theoretically, couldn't I find out what's the temperature that I turn up on any given day, and the temperature is between 61.2 and 68.5, right? I could even do that, couldn't I? You know, I probably want my calculator handy, but I could do it. Any questions? Are we good? None from Raven? Jamie, you're good?
Yes, sir.
What about you, Adrian? Are you okay with this? Adrian, can you hear me? You might be on text, I guess. Did you hear my dog there? What's up, Billy? Oh, we're going to have a dog interruption for a minute. Yep. There we go. Up. Ah. When I'm talking, he doesn't realise that I'm on Zoom, and so he wants attention for a minute. Right? Okay, that's it. We'll give you a little walk. Whoa. Come on. There you go. Excuse me. Demolishing the place. Well, what I'm going to do for the next few minutes.
Hello, sir.
Yes, question.
Sorry, I have a question. So,
Yes.
So the probability of 61 between X, or how do you read that one? 61.
This one, you read this. This is how I would read it out loud. It's a probability that X, whatever X in this case, my story is the temperature, is between
61 to 64.
Yeah.
Okay. So why is it 3? Because there's 3
yeah, there's
portion.
three, yeah, if you go 61 take away 64, if you find the distance between them, isn't that 3 right?
Because there's 3 portion of it. Like...
Yeah, 64 take away 61 is 3 degrees.
Oh, okay, got it.
Right, and then the height is still 0.1. So the area of that piece of the pie, right, that cake, whatever right, my story is going to be in this case 0.3. So you're always looking in continuous variables of this type of question for the area of the thing, right? That's kind of the way you're going to go.
Yep.
Right. So let me see if I can find our guys. That looks like it. I'll kick back in. Bit concerned about Adrian. He hasn't gone in. Keeled over. Adrian, are you with us? I cannot see any sign of life. I wonder if he's getting through. Okay. What I'm going to do now is we've got about 6 or so minutes to go. is look at what the homework questions look like, because sometimes the homework questions can make life, they ask a question in a way that's maybe not clear. You know the answer if they'd ask it in a better way, but they don't always do that. So here is, I hope, can you see the 146 stuff that I'm showing?
Yes, sir.
Okay, so I'm going to click on question 1 and we'll just go through my version. Now, the one up here says, determine whether each of the following variables would be best modeled as continuous or discrete. So it's a pretty quick question. And it looks like they're giving us 5 choices, but they only pick one of them. So let's go through all of them. Suppose the variable was the number of points scored in a basketball game. Continuous or discrete?
All right. Can you repeat that, sir?
Yeah. The number of points scored during a basketball game. Is that continuous or is that discrete?
Discrete?
Yeah. You get 22 points, you get 25 points, right? You get,
Yeah.
I don't think you can get 22.123 points. I've never heard of it if they could. Right. The weight of a steak.
Continuous.
Yeah, agreed. The number of people in a restaurant. It has a capacity of 100, but that doesn't really matter. The number of people in a restaurant.
Discrete.
Discrete. The number of hits a website gets in a day.
Discrete.
Yeah. And lastly, the time it requires to download a file.
Oh, that's continuous.
Right. And you begin to get the feel that certain things are pretty obviously continuous.
Yeah.
To me, weight, height, measurement, length, things like that are almost always continuous. And discrete things tend to be very specifically, you're this or you're that, right?
Yeah, like
you can have
exact
12
number.
Yeah, it's an exact number. It's probably a much clearer way of saying it. Yeah, exact number. Now, this next question is talking about continuous or discrete, so I'll just skip by that. We've got the gist of this one. Right, I don't know if I can make this bigger or not. Can I do that? Can you see this very small thing here? Is it readable?
What's that?
Oh, can you see, for starters, you might not be able to see it. The sharing can be weird. Can you see question 6.15 and it's a little chart?
No.
No, okay, so I think what I'm going to have to do is going to go out and then go back in and we'll share it again. There, you should be seeing it now. Is that right?
Yep.
Okay, I'm just going to see, and I don't know if I can do it, and if I can, I will. I'm trying to see if I can make this thing bigger. Not in any obvious way that I can see here. Okay, we'll just do with what we've got. Ah, wait a minute. Ha ha ha. Oh. Okay, that looks like as big as I can get it before it disappears.
You can click, sir, the box with the arrow up.
Ah, yes, well done. Shows you I don't do this homework, I just do the questions. Right, now here is one of those funny little charts, you know, the one with the line and the dot at the top?
Mm-hmm.
Right, now this is a throwing a dice, right, throwing a die is just a single for a dice. So you throw a dice and you get a 1, you get a 2, a 3, a 4, a 5 and a 6, and you're just doing the probability of it. So let's do this. The number 1. The chance that I roll a dice and got a 1, at least in this particular story, happened 0.1 of the time. So that's its probability. 2 happened about 0.2 of the time. There's a 3, there's a 4, and there's a 6. So can you see that you could read off these numbers and then fill in what's essentially a table with the probabilities? When you finish with this table, this is your probability distribution table. There's the probabilities, and this is what they're equal to.
Can we try to do it, sir? Like for 1, so is it 1%?
Okay, for number 1, you can write in the decimal 0.1, which is 10%.
Okay.
But let's do decimals because I think that's what the book likes. 2 would be 0.2. 3 would also be 0.2. So is 4 and 5. And finally, 6 would be 0.1.
Oh.
Now, if I do a quick add all those answers up, do they add up to 1 the way they should?
Mm-hmm.
So I know that I haven't screwed up.
Mm-hmm.
Or I know that the table, the picture they gave me is a valid one. I guess they could give you a picture like this and say, is this a probability distribution? And you'd have to say that plus that plus that. Yep, it adds up to 1, it's good. But suppose they gave you a picture and it added up to 0.8. Then your answer would be, no, this cannot be a probability distribution.
Yeah.
Or if all of them added up to 2.2, it would be the same no again. Does that question kind of make sense of what you've been asked to do? Any questions? Or we can
Sir?
move on? Yes.
Sir, so probability is between 0 to 1, right?
The probability is exactly 0.1. So if you throw a dice, the chances that that dice is a number 1 is 0.1.
Okay, so probability is 0.1 and 1.
Right. So in this guy here, see this box? Can you see my mouse? I don't know if you can see my mouse.
Yeah.
Right. The number of spots, 1. Probability that happened, 0.1. Number 2, probability it happened, 0.2. Number 3, also 0.2. 4, 0.2. 5, 0.2. And finally 6, 0.1. So your probability distribution will have 0.1, 2, 2, 2, 2, and finally 0.1 at the end. We cool?
I mean, sir, the total.
The total adds up to
1.
1.
Yeah.
Yes.
Yeah.
So if you add up 0.1, 4 lots of 0.2, and finish with an add 0.1, it does add up to 1.0, right? It adds up to 1.
Okay.
Are we good?
Yes, sir.
Right. See if we can zoom through another one. Here's a probability. Tell me what picture it is. Then that's pretty clear. Right, this one here, when a certain type of thumbtack is flipped, the probability of it landing up is 0.66, and the probability of it landing down is 0.35. Okay, so this is going to be my last question for today, and I'm just going to write down what those numbers are so I can use them. So you throw a tack and it lands up, which would certainly be the dangerous way, is 0.66, and the probability that it lands down is going to be 0.34. And this is 6.1.7. So it then says choose the correct answer below and fill the answers in the boxes. We're being asked, well, they give you a whole set of ones, so I'm just going to pick one of them and look at it. One of the choices was the first one, which says the probability of getting an up and a down and the probability of getting a down then an up, right, are equal. And let's see what we get. Close this off. Right, let's just suppose I wanted to find the tack. The first time was up, the second time it was down. We can separate this into the probability of an up times the probability of a down. Now, the reason we're allowed to do this is that if you throw a tack in the air and then you pick it up and you throw it again in the air, the two events are totally independent of each other. They don't affect what's going to happen next, whatever happened first time around. So when that's the case, you're allowed to use the rules called the multiplication rule. Now, an up is 0.66 and a down is 0.34. So the probability of that particular combination happening is going to be 0.66 multiplied by 0.34, and I get 0.2244. Are you happy about how I calculated that particular double event?
Yes, sir. It's like the same with probability A and B. something like that.
Yeah,
The
it is.
previous example. Yeah.
It's exactly like that. You're right. No, just to finish, I'll do one that's not in that list. Suppose you threw the tack 3 times and you wanted to know what's the probability that you end up with the pattern. It was an up, then it went down, and then lastly it was down again. Well, that is an up times a down times a down, right? We can use that multiplication trick.
Mhm.
And the up is 0.66, this is 0.34, and finally this is 0.34. So I'll just finish off with this one. So 0.66 times 0.34 times 0.34. And I am looking at a very small percentage, 0.076. So all you need to do is read the question, because sometimes they say to 2 decimal places, to 4 decimal places, and make sure you round off accordingly when they say that. Okay, then are we all cool?
Yes, sir.
Right. So just a reminder, I know it's a while away, but today or this week is all going to be chapter 6. I'm going to have another meeting where we'll get to look at what's called the Z-scores and normal distribution, and that's a biggie. And this Sunday you're getting your 3rd test, and it's going to be on chapter 5 and 6. So we're getting close to the end. Right? So keep your eye on the ball, and we're almost over. Well, that was nice. I have another meeting that I have to get to, so I'm going to have to say a pretty quick bye-bye. Thank you for turning up.
Thank you, sir. Bye.
Bye. Bye-bye, Robin. Bye-bye, Adrian.
Thank you.
Ah, Adrian, I got you. You are alive. You just can't communicate. Okay. Well, thank you for dropping in as well, Adrian.
Of course. Thank you, Professor.
Okay. Bye-bye.